obtaining a PhD in computational neuroscience from the University of Cambridge and a master's in machine learning from UCL, he set about building machine medicine, a company that marries both clinical and engineering perspectives to what, in a manner that's compatible to what clinicians are already doing and making it more objective. His topic today is computer vision-based motor assessment in movement disorders.
Thank you very much, Katie. And Katie's right, I did also invent machine learning too, so I'm not going to be too long. This is going to be much less taxing than our previous talk, which was excellent and I enjoyed very, very much. I'm not going to pitch machine medicine to you, but I am going to tell you at a fairly high level about the technical work we do at machine medicine and why we do this work in the longer term. So at machine medicine, what we've been focusing on for the last 5 years or so is computer vision-based motor assessment. And a perfectly reasonable question that we do often get from investors when we're talking about how we're interested in BCI-based systems is, well, why are you studying movement if you're so interested in machine neural interfaces? And I think a nice way to understand why we do so is because movement and the motor activity of animals is arguably the fundamental reason why nervous systems exist, and for example why trees don't possess them. And a very nice example that exists in nature is does anyone know what this is? This is the larval form of a sea squirt. So this is an animal that in its larval form is mobile. It is a lot like a tiny tadpole. This is microscopic size. It's only perhaps a millimeter long or something at this stage, but it has a brain, or at least a nervous system that it uses in order to move about the world. And what it's looking for is a place to attach itself. And once it finds a suitable location to attach itself, it leaves its larval stage and turns it to an adult stage, and it no longer moves around, and so it auto-digests its own nervous system or its own brain. It's being compared to acquiring tenure for academics. But the point is, it no longer needs it because it doesn't need to move around anymore. So it simply auto-digests it. And so arguably the fundamental output of nervous systems is behavior and movement. And so if we want to understand how neurons and very large populations of neurons like the human central and peripheral nervous system are computing, then we should really understand what they're trying to compute. And this is how we currently, when I was working as a clinician, this is how we still do assess patients from a motoric perspective. And you can see it's very it's very low tech and totally unscalable. We're interacting with a patient, and the person in the corner is recording the results. And I was doing a lot of this, and this is one of the things that made me start to think about, is there a way of understanding behavior in a more data-driven and a more scalable kind of fashion. And so other people have thought about this for a long, long time, and they've come up with various solutions. And I think the accelerometer-based approach to measuring behavior is a classic kind of engineering solution. For example, when engineers are monitoring whether or not a bridge is moving too much, they often attach accelerometers as a way of measuring movement. Accelerometer is a very natural way to think about it. However, this accelerometer only tells you about your index finger, so maybe we should attach another accelerometer. This one will tell us about the wrist, and maybe another accelerometer, and maybe at the end of it we'll have enough accelerometers that we'll be able to understand exactly what's happening throughout the entire body. Well, in machine medicine, we think that that's probably not the best solution, and we have a different approach. We believe that computer vision offers a far richer approach to measuring and understanding, ultimately, movement. As well as the machine learning that I'm going to talk about, I want to, first of all, start off by telling you about the software that surrounds our machine learning sort of kernel, if I can call it that. So we have a set of applications, mobile applications that are available on iOS and Android, and it's a BYOD model. So they're installed on a user's own device. That might be a clinician who would have their own tablet in the clinic, and they would install our software and record the video, or a patient at home using Kelvin Reach, and this is a This is a little chap here, Kelvin, who pops up when they open the app and tells them to do this or that, and then video is recorded, and it all gets uploaded automatically to the cloud where it's stored. This is really, I believe, a crucial part to kind of turning this stuff from just a sort of nice piece of research or a nice theory into an actual usable product. This is what actually, these data capture tools are what actually make this possible, and I'll mention a bit later the kind of potential applications that having this kind of paraphernalia around the ML side of things enables. But to get back to the machine learning side of understanding behavior, this is our approach is actually can be understood relatively straightforwardly, I think. If you think about what a video is, it basically just consists of multiple frames at regular intervals, and over the course of over a period of time that tracks or captures the information around some kind of movement, in this case for a patient. From that, using a branch of computer vision called pose estimation, it's a little hard to see here, but we're tracking the key points on an individual's body from his knees to his hips, all the way down to the individual fingers. From that, we get this high-dimensional time series, this multivariate time series. And then the sort of challenging part is to identify the parts of that time series that are really relevant. And here, for example, we're just extracting the frequency of finger tapping and noticing that identifying that there is indeed a difference between the frequency at which people tap their fingers when they're off medication versus on medication. They do it faster when they're on medication. These are Parkinson's patients, of course. And then we can take those biomarkers or features that we can identify from this movement and put them into machine learning models in order to get a sort of composite or a final end estimate that would be comparable to what a clinician might be doing. Think of this whole system as basically emulating what a neurologist's sort of visual cortex and perhaps some higher areas is doing when he or she monitors a patient doing this. So that's the kind of that's the sort of the basic model. But if you think about it, we can only do this once we know that the patient is doing this particular action or finger tapping or walking. And so one of the things we've had to build at Machine Medicine before we're able to do the algorithmic motor assessment is activity recognition. What I've told you about is just this part here. And the other part that's relevant is this activity recognition. So in order to make this scalable and, like I said, take advantage of applications like Kelvin Reach, be able to record, say, across hundreds of thousands of patients and not have to have somebody go in and label that data, we need to be able to identify when they're doing this or that particular action. So this is from a paper that that was out on one of the archive journals, but will soon be out in its proper published form, and basically this is how it kind of works. So you can see here there's not actually a patient, but one of us pretending to be a patient performing a particular action. What you can see here is the algorithm recognizing that they're performing here's right hand movements. Not sure what's going to happen next, but we'll see. So there's right hand pronation and supination. So you can see that we can actually, and this is a long video, I'll stop it in a sec, but you can see we can actually do a pretty good job of recognizing when a patient is doing a particular action. And then if we take those two components together, the motor assessment that we were doing in terms of estimating the disease severity and the activity recognition together, then we can end up with a system which is actually able to assess a patient in a fully automated way. It's fully automated, of course, somebody's recording this video, but once the video has been recorded, then the algorithm is taking the video, identifying when they're performing the particular action, and so that's what you can see here. Here it's saying the patient is toe tapping now. There, once the toe tapping is finished, the motor assessment algorithm kicks in and says this patient's doing that in a normal fashion, so it scores a 0. Anything 1, 2, 3, or 4 would be various degrees of impairment. And you can see too that it's kind of doing something sensible, right? Because here's the signal from the patient's foot, and you can see it's a smooth, periodic, sinusoidal signal. Whereas when the patient is slightly impaired, here they're doing the same action, toe tapping, but now on the left side. you can see that the signal is still periodic, but has these hesitations which indicate that he's not able to maintain a nice sinusoidal pattern of movement, and the algorithm's basically able to measure that and identify that that is indeed a problem. So I've just shown you particular instances of this happening for, say, something like hand movements or finger tapping. One of the things we subsequently then went and did is said, well, how about if we put a bunch of these scores together? Can we characterize the whole body function of a patient in a sensible way? And it turns out we can. This is from a paper that we published in Nature Parkinson's Disease earlier on this year, which we're very pleased about. And what we're showing here is if we take 5 different items, so 3 items of the upper limb, finger tapping, hand movements, and supination, pronation, and 2 items regarding the lower limb, toe tapping and leg agility, and we sum those scores up. So the model is giving a score, an individual score for each of those 5 items, and then we sum them up for a particular patient. And then we look at what the clinician said as well. You can see perfect correspondence would be all of the points would fall along this line. We wouldn't expect to see that. Even if 2 expert clinicians were being compared, we'd expect there to be a bit of noise around this. But what you can see is it's actually a very good correspondence with what the clinicians say. And these areas up here, this would correspond to a clinician saying the patient was very impaired, but the algorithm saying the patient was fine. And down here, which would correspond to the clinician saying the patient was fine, but the model saying the patient was profoundly impaired. There's basically nothing here, right? So it doesn't make big errors like saying the patient's fine when it's not, and saying the patient's not fine when in fact it is. And here we're just showing the same kind of thing. These are what are called the residuals, so that the errors that the model makes, and these red lines indicate sort of clinically significant boundaries. So anything within here is the kind of magnitude that we'd expect to expert clinicians to regularly disagree by, and anything outside is something that's probably clinically significant. So in future work, we'll try and push this distribution inside the red lines as much as we can. And then this is what we're showing here is these are 2 things called confusion matrices. And a confusion matrix, basically, if a perfect system should have all of the color on the diagonal. And the point here is that if we take the activity that's being identified by the algorithm, and if we take the activity and we identify it using human labelers, so these are people like you or me who can watch the video and say, yep, they're definitely hand tapping there, hand movements or finger tapping there, and then we let the model do it, then essentially the model and the humans perform to the same level. So we don't lose anything by letting the model identify when the patient is doing the assessment. And this is just to sort of establish the fact that we're not actually, by allowing the algorithm to identify when the patient's performing an action, and also by allowing the algorithm to score the patient in terms of how impaired they are, we're actually achieving something at least very close to human level performance. And these are just basically establishing the same thing. There are a couple of small significant differences, but basically the 0 line is that they're doing it in the same way, and all our data is very, very close. Now, that's all well and good, but what is any of this good for? So I've mentioned a couple of things. One is that we can do at-home clinical monitoring between visits. Typically, a patient with Parkinson's disease, if they were lucky, might be seen every 4 to 6 months by their clinician. Our system allows them to be seen as often as they choose, as it were, at least to be assessed as often as they choose, perhaps daily or weekly. Perhaps more significantly, with a system like ours, one could undertake massive sightless clinical trials. If you think about a typical Parkinson's disease trial currently, it might consist of several hundred people, say 250 people, something like that, and it might be conducted over 3 to 4 years, right? And the reason for that is because they're looking for an effect size, and it's been powered that in order to find an effect size this big over 4 years, you'll need, say, 250 people. A system like ours would allow you to have a trial that had, instead of 250 people, 100,000 people or 250,000 people, and you could pick up a divergence between an intervention group and a control group in, say, 3 months rather than 3 years or or more. But then the kind of stuff that we're really super interested in is more around this kind of thing, like closed loop neuromodulation. And I'll just try and give you a flavor of what I mean by that. This is the kind of neuromodulation that we mostly work in. Most of the clinical sites that use our system are deep brain stimulation sites, and they put these kind of systems in. These are deep brain stimulation systems. It's very much like a cardiac pacemaker that many of you will have heard of, which tends to go in the same place on the chest, except that instead of the lead going into the heart and controlling the abnormal rhythms in somebody's heart, the lead goes into the deep nuclei of the brain, usually on both sides, and helps to control the dysregulated rhythms that underlie things like a tremor or slow movement, bradykinesia, that we see in Parkinson's disease. And you can't get a very good look at it here, but it's actually quite a complex structure to the electrodes that are put in to the brain, as you can sort of see better here. These are all of the commercially available deep brain stimulation electrodes here, and the black is essentially the contacts where they're electrically active or at least interfacing with populations of neurons. And the thing to appreciate about this is the possible combinations of stimulation parameters that you can have here are absolutely phenomenal. If you take these ones, these leads, this is a modern lead. It has multiple contacts, but it's much more similar to what the first kind of monopolar leads were like. So monopolar leads literally had a single contact, so you had essentially a single circuit that was creating something close to a spherical volume of stimulation. These leads here have been constructed so as to be able to sculpt a three-dimensional volume of stimulation within the brain. The idea is that you can stimulate the neurons that are responsible for a therapeutic effect and spare populations of neurons that are responsible, say, for side effects. But the downside of that is that now these things are incredibly complex to program. You can change the frequency, the amplitude, the relative amplitudes of all of these things. So this is a very challenging problem. And the way it happens at the moment is that people have one of these systems put in. It takes about 6 hours to put it in surgically, and then it takes about 6 months to program these systems. They have to go and see the neurologist month after month. They'll turn the frequency up on this contact or down on that one, and then send them away for a month, and they'll come back and tell them how they've been. And then I'd like to show you kind of what we're doing in this. I'd like to just bring your attention to a little bit of animal data. So I've showed you the pose estimation that we've been using. This is some pose estimation that's been done on animals in the Mattis lab in Switzerland. And here they're using very similar technology in order to track the movements of mice. And as you can see, they do a very good job of it. But what's even more interesting is that they've then taken the movements of a mouse up and down a track like this, and they've recorded at the same time the intracranial neuronal activity of actually about 120 neurons at the same time. So they've got interesting data here, right? They've got the behavioral data of the position of the mouse on this track, just in one dimension, but that's sufficient because it's narrow. And then they've got the neuronal data, right? So at the moment, this data is very complex. It's at like 120 dimensions of neuronal behavior, and then another dimension for position. So it's 121 dimensional data, which is very difficult to understand. But actually, what they're able to do using neural nets is that they can find a low level manifold, a low level dimensionality reduction that allows them to express the essence of the behavior in a much lower dimension here, 3 dimensions, I suppose, or if you think of it actually on the surface of the sphere, 2 dimensions. And so that's a rather nice framework in which to try and understand neuronal data and behavioral data. And what's cool about what's happened recently in the DBS field is that where the stimulators that I've shown you previously, most of those leads that relate to pulse generators, they're typically only stimulating, they're not recording. But recently, Medtronics brought out a system called the BrainSense system. It's the Percept system. It has BrainSense technology. And what that is a deep brain stimulation system that can stimulate populations of neurons within the brain but also record the local field potential at the same time. This kind of gets back to some of the stuff that Dimitros was saying a second ago, because that local field potential, although it's a gross representation of the activity of many hundreds of many millions of neurons, there's no doubt that it carries information about the proper functioning of those neurons. And we're very gratified to recently have been awarded funding to work with the University of Amsterdam and and Medtronic in order to synchronize our own rich motoric characterization of patient movement with the brain sense recordings of local field potentials. And what we hope to be able to do with that is characterize the neuronal and the clinical data in much the same way as I showed you with the mice, but to use that in order to optimize the parameters of the deep brain stimulation systems in order to achieve the maximal clinical outcome for the patients. And so with that, I'll just say that we are growing quite rapidly at Machine Medicine, and if you like what we're doing and you're interested in it and you feel you might be able to contribute, then we're very happy to talk to you about it and perhaps work with you in the future. Thanks a lot.
Thank you very much. We now have some time for Q&A. If you have any questions, raise your hand and I'll pass the mic to you.
Where's the pizza? It's just there.
Thanks, Jonathan. Really exciting. That video that you showed with your colleague moving, and you had a graph on the right which detected that movement. I noticed at one point when they were not moving, you had some kind of baseline signals. Can you tell us a bit more about that?
About the no action here?
Yeah, when there is no action. And to what extent, can you get an absolute reference across patients, for example? I mean, is that kind of a baseline signal that's always going to detect?
So what we're basically trying to do here is if you think about it, sometimes, I mean, I think it's really interesting because kind of the competitors that we're often compared to are people that are doing things like using watch-based systems, and so they're measuring ambient or they're measuring kind of normal everyday activity, and that's great. And actually, integrating that data is one of the things that we've been doing recently. However, the reason why clinicians do these kind of things, like getting people to do this and stuff, is you're basically perturbing the system, right? You're challenging the system in order to uncover weaknesses in it, essentially, right? Which you don't always see when you're just letting people go about their ordinary behavior, because typically people take a sort of energy minimum route and they try not to challenge their own physiology, whereas that's exactly what's happened here. So what we're trying to do here is we're trying to recognize when the patient is undertaking one of those challenging exercises, so that we can, as it were, focus the light of the algorithm on that and gather that data in that sort of information-rich time, that period when they're actually doing that activity. So for us, kind of like no action doesn't really mean they're doing no action. They could be dancing a jig. It just means that they're not doing something that we recognize as a kind of a sort of physiological challenge to someone with Parkinson's disease.
Yeah, very interesting work. So do you mind saying a few more words about the use of DBS? Or, for example, what would be the target area might be looking at, and maybe how you would use the recordings, the STEAM, in concert with these biomarkers, motor behavioral biomarkers?
Yeah. So, I mean, we're really excited about working with Medtronic, but I think arguably, one of the things that people have in their mind in the field, I think, is that somehow by measuring local field potentials, we'll be able to characterize the kind of global neurological function of the brain. And I really don't think that's plausible at least with the systems like Medtronic's system that we have currently. But it definitely does carry some information about their clinical function. But what we really want to bring into this collaboration with Medtronic is we think these problems have actually been addressed by companies like Netflix and Amazon over the last 20 years in the context of recommender systems, right? And if you look at something like, take Netflix, for example, and look at the history of how they developed their own recommender systems, which now drives about 80% of viewing behavior on Netflix, right? They started off trying to build explicit models of their users. And I remember when I signed up for Netflix I don't know, 15 years ago or something, they gave me a huge questionnaire of items where I had to say, how much do you like each of these categories? And there was like, action, romance and all that. And it was very, very boring to try and fill out all of these 50 rows, and also didn't work very well. So what Netflix switched to was a system where they, instead of trying to characterize you and build an explicit model of you, they would try and find other users who were similar to you. And by doing that, they were then able to leverage, essentially use other users as a model for you and leverage their viewing behavior in order to make recommendations for you. And I think there's a great opportunity in neuromodulation, and in this context, for example, for us to take a similar, as it were, sort of mechanistically agnostic approach, where we try and leverage those big data-based systems, such as the ones that Netflix have used, in order to do a similar kind of thing. So, and the beauty of it is that we don't need to have a full understanding of the anatomy in order to be able to make accurate recommendations to people. We just need to be able to find regularities and similarities between different patients. And that could be true for the local field potential, or it could be true for their pattern of movement disorder, or it could be true for their, even things like their cognitive, higher level cognitive interests and so forth. So yeah.
Last question.
Okay, so I actually have like 2 half questions. It's one question. It's like 2 questions. So one of them, how much do we trust the clinicians? Because in some medical fields, like algorithms already do better than the clinicians. So if you have like a ground truth, which is not that good, then maybe what you think is an outlier in the algorithm, it's already doing better. So that's the first question. The second one is like in the composite scores. I think it's like it was just a simpler summation, right? Like there was no weighting. So I would be like curious, like how valid it is, because maybe some of the movements might be like more relevant than other movements.
Well, there's weighting in the model, right? So the model weighs different elements differently, and probably the clinician does the same thing, right? So there's probably weighting on both sides, probably. Sorry, your first question was, remind me, sir. So the clinicians, are they doing a good job? Honestly, I think they probably are, and I think they're doing an okay job at least. And in a sense, I think it's not that important, because the real advantage of our technology, people often sort of alight upon the objectivity of our approach, and there's no doubt that it is objective and reproducible in a way that human behavior can never be, I think. There's also an argument from kind of like the wisdom of crowds that actually, even if one way of thinking about how the model works is basically just taking a weighted average of all the clinicians that have put data into the system, right? And the sort of the literature from the wisdom of crowds, is that if you take fairly noisy judgments from people that are nevertheless somewhat accurate and put them together, then you can end up with a very accurate estimate as long as they're roughly unbiased. So that's one way of thinking about how the algorithm can actually become much less noisy than all the inputs that it's having. It does rest on the assumption that they're not biased, but just noisy. But the real advantage of the technology is that it's scalable, right? If you think about doing like a massive clinical trial of 250,000 people, why couldn't you do that? Well, the main reason is because it would cost you tens of millions of dollars to pay neurologists to watch video for 250,000 people, right? Whereas this system can do it for a few tens of thousands of dollars on AWS, right? So it's an order of magnitude improvement in scalability, or 2 orders of magnitude, arguably. And the same goes for things like DBS systems. There we're just looking at sort of across space, but actually with DBS systems, instead of the paradigm that we want to move to is instead of the patient going to see a clinician once every month for 6 months, which is a clinician-centric model of programming, the patient can sit down in front of their, their Netflix system every day and do their assessment, and that data gets put in on a daily basis. So that's a patient-centric model of programming, just like Netflix uses that. There's nobody at Netflix that programs anybody, any individual's account. They build algorithms that allow you to program your account with your behavior. And that's the kind of paradigm shift that we think our technology is enabling.
Thank you very much, Dr. O'Keefe and Dr. Hypnosis. Can we have another round of applause for them? So thank you very much for coming to the event. I hope you enjoyed your time today. If you're looking for a career in computational medicine, machine medicine is a very good place to work at. We are looking for future team members. Please speak with me if you're interested. Also, since this is our first event, we appreciate any feedback that you may have. There are QR codes on the table, so please scan them and it will lead them to the survey. Lastly, perhaps the most exciting part, we have prepared a small selection of pizza and drinks on the tables behind you. I hope you enjoy your Wednesday evening.